Welcome to today's Explainer. We're diving right into a fascinating classroom lesson on those massive, invisible rivers of air speeding high above our heads that secretly dictate our daily weather. Think about it for a second. What actually decides if you're going to need an umbrella today or a heavy winter coat tomorrow? It's not just your local clouds. It's this massive, interconnected global engine. Here is our lesson plan for today. We'll start with the Earth's weather engine, meet the jet stream, cover the water cycle and pressure, look at fronts and changing seasons, and finally wrap up with some real-world jet stream impacts. Let's get right into it.
All right, Section 1, the Earth's weather engine.
So our Earth's weather engine is driven by a few huge factors. Our planet is tilted, the sun heats it unevenly, blasting the equator with direct energy while kind of glancing off the poles, and absolutely crucially, the planet is constantly spinning. To understand this spinning weather engine, we really have to define the Coriolis effect. Basically, it's an apparent effect produced by a rotating frame of reference. It makes objects traveling long distances appear to move in a curve instead of a straight line. This is the main reason why our winds curve and weather systems swirl predictably across the globe, rather than just shooting straight north or south. Think of it this way. Imagine standing at the North Pole and tossing a ball straight to a friend at the equator. Well, the Earth rotates eastward, right beneath the ball while it's in the air. So when the ball finally reaches the equator, it lands somewhere to the west of where you were originally aiming. This fictitious force deflects our prevailing winds to the right in the northern hemisphere and to the left in the southern hemisphere. It's strongest right at the poles and actually hits exactly 0 right at the equator.
Moving on to Section 2, meet the jet stream.
When you combine that uneven solar heating with that curving Coriolis force we just talked about, you get these absolutely incredible, high-altitude rivers of air. They live about 6 to 9 miles above the Earth, right near the top of the troposphere. The jet stream is hundreds of miles wide, a few miles deep, and it races at insane speeds. We're talking winds often exceeding 100 miles per hour. These currents are constantly flowing around our spinning globe, basically acting like the fast-track highways of the atmosphere. Fascinatingly, there isn't just one jet stream up there. There are actually 2 main types in each hemisphere. First, we have the polar jet stream. This is the stronger of the two, and it sits exactly at the boundary between freezing polar air and warmer mid-latitude air. Then there's the subtropical jet stream, which is a slightly weaker wind near the boundary of warm mid-latitude air and hot equatorial air. These distinct wavy streams act like massive invisible walls that powerfully separate cold and warm air masses all over the globe.
Okay, Section 3, water cycle and pressure.
So how do these fast-moving walls of wind interact with all the moisture in the atmosphere? Well, it all starts with the continuous movement of water, which is driven entirely by the sun's energy. The sun heats liquid surface water, causing it to evaporate. That water vapor then rises up into the atmosphere, transitioning from a liquid to a gas, where it joins that complex web of atmospheric pressures and winds we just discussed. Now, this might surprise you, but water molecules are actually lighter than the molecules of nitrogen or oxygen that make up the vast majority of our air. Think about that for a second. This means that very moist air that is just packed with water vapor, is practically lighter and less dense than completely dry air. Because it's lighter, that moist air creates low-pressure systems that rise high into the atmosphere, eventually cooling down. If we follow the journey of a raindrop, we see this exact physical process at work. Water vapor rises and cools as the atmospheric pressure drops. Then, that vapor condenses around tiny particles, like dust, turning back into liquid droplets to form clouds. Finally, when those droplets gather together and get just too heavy, gravity pulls them down as precipitation, rain, snow, sleet, or hail. And what guides these massive, water-carrying, low-pressure cloud systems around the world? You guessed it, the jet stream. It acts like a giant global conveyor belt for all our moisture.
Let's dive into Section 4, fronts and changing seasons.
When these jet stream-guided air masses actually collide down here on the surface, we get what are called weather fronts. In a cold front, dense, heavy cold air actively wedges itself right under lighter, warmer air, pushing it rapidly up into the troposphere. This violent lift is what often causes those dramatic thunderstorms we see. On the flip side, in a warm front, lighter warm air gently slides up and over a retreating cold air mass, typically bringing low stratus clouds and steady, lingering rain. So the absolutely crucial point here is that the jet stream is fundamentally responsible for the seasonal temperature shifts we feel in our own backyards.
When this wavy river of wind violently dips south, it drags that frigid polar air mass right down with it. And boom, we experience a harsh blast of winter weather. Conversely, when it rises north, it allows warm tropical air to surge upwards, making our local weather much, much warmer. It really is the ultimate gatekeeper of our seasons.
And finally, Section 5, Real-World Jet Stream Impacts. Have you ever noticed that a flight from New York to London is significantly faster than the flight back? Well, for commercial aviation, the jet stream is a massive operational asset. Pilots actively chart their long-distance flight paths to ride these high-altitude, 100-mile-per-hour winds. Flying with the stream completely boosts flight speed and maximizes fuel efficiency, saving airlines millions of dollars and cutting down on your travel time. It's literally a built-in tailwind provided by the Earth's weather engine.
And it's not just airlines tapping into this physics. Our daily operations are deeply intertwined with these atmospheric rules. For instance, a military sniper taking a long-distance shot actually has to calculate for the Coriolis effect. A deflection of just a few centimeters caused by the Earth rotating beneath the bullet can make all the difference. Or look at massive tropical cyclones. Because the Coriolis force is exactly zero at the equator, hurricanes literally cannot circulate there, meaning they never cross the equator. No way around it. Nature and human ingenuity alike are totally bound by these invisible forces.
I want to leave you with this final provocative thought. The entire engine we just mapped out together, the fast-moving jet streams, the guiding of storms, the separation of warm and cold air masses, is fundamentally powered by the temperature difference between our hot equator and our freezing poles. So as global temperatures shift and the poles warm, how will these invisible walls of wind behave? It's a huge puzzle that atmospheric scientists are racing to solve right now, because as the jet stream changes, so too will the entire weather engine we rely on. Thank you so much for joining me on this explainer, and keep looking up.